Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring what lies above and below our familiar Milky Way galaxy, the enigmatic galactic halo, and the vast cosmic void beyond its luminous disk. Before we gently immerse ourselves in these profound cosmic structures, I would like to know where you are at this moment. Perhaps you are nestled in a window seat, watching the world drift by as a night train glides softly through the landscape, or perhaps you are gazing up at the quiet expanse of the moonlit sky from a secluded balcony. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The visible splendor of our Milky Way galaxy, a majestic spiral disk teeming with hundreds of billions of stars, vast clouds of gas, and intricate lanes of dust, is, in truth, merely the most luminous part of a far grander and more mysterious cosmic structure. Beyond the familiar glowing arms where our own solar system quietly resides, extending far above and below its luminous plane, stretches an immense, roughly spherical region known as the galactic halo. This halo, often imagined as a faint, ethereal shroud, is in reality a colossal cosmic domain, dwarfing the bright disk in sheer volume and gravitational influence. While the disk itself might span approximately 100,000 light-years across, the halo extends for hundreds of thousands of light-years in every direction, forming a spherical envelope, a vast gravitational sphere of influence that embraces and contains the more visible components of our galaxy. Within this immense celestial sphere, the distribution of visible or baryonic matter is remarkably sparse and ancient. Here, scattered across truly immense distances, we encounter some of the oldest stellar populations in our galaxy, remnants from a time when the Milky Way was still in its formative stages. These include isolated individual stars, often referred to as population 2 stars, which are notably deficient in heavier elements compared to the Sun. Born in a younger, purer universe, they drift through the halo's vast emptiness, solitary wanderers, their long, unhurried lives bearing silent witness to billions of years of cosmic history. More prominently, the halo is home to globular clusters, dense, spherical collections of hundreds of thousands, sometimes millions, of these ancient stars, bound tightly together by their mutual gravity. These venerable clusters, perhaps 150 to 200 of them, orbit the galactic center in elongated eccentric paths, like cosmic bees swarming around a distant unseen hive. Each cluster is a tiny, self-contained universe of primordial starlight, a fossil record of the galaxy's earliest epochs, their very existence offering invaluable clues to the Milky Way's turbulent and chaotic youth. These stellar populations, though luminous, contribute only a small fraction to the overall mass of the halo, serving as distant markers in its otherwise dark expanse. But beyond these visible, albeit faint, stellar populations, the true nature of the galactic halo begins to reveal its profound and enigmatic mystery. The luminous stars and gas we painstakingly observe account for only a small fraction of the halo's overall mass. For decades, astronomers have meticulously observed that galaxies, including our own Milky Way, rotate at speeds that simply cannot be explained by the gravitational pull of their visible matter alone. If our galaxy comprised only the stars and gas we can detect with our telescopes, its outer regions would spin so rapidly that stars, gas clouds, and even entire star clusters would be centrifugally flung into the cold, empty reaches of intergalactic space, much like water droplets from a rapidly spinning wheel. Yet they remain steadfastly gravitationally bound, moving in a harmonious, stable, and enduring dance around the galactic core. This profound and persistent discrepancy, this missing gravitational force, leads us to the most significant, yet entirely invisible, component of the galactic halo: dark matter. The dark matter halo is understood to be the primary, dominant gravitational structure of our galaxy, providing the unseen scaffolding, the colossal ethereal framework that holds the entire visible disk together. It is believed to consist of a diffuse, roughly spherical distribution of exotic, non-baryonic particles. These particles are thought to interact with ordinary matter only through gravity, meaning they do not emit, absorb, or reflect light or any other form of electromagnetic radiation. This fundamental lack of interaction is precisely why it is termed dark. It remains utterly invisible to all our conventional telescopes and detectors. Its pervasive presence, its immense silent influence, is inferred solely through its profound gravitational effects on the visible matter within the galaxy, a cosmic whisper of its grand existence. Imagine attempting to comprehend the intricate, synchronized movement of a vast school of fish, only to realize that their complex, organized dance is predominantly governed by an invisible, massive ocean current that flows silently around and through them, dictating their every turn. The dark matter halo functions much like this unseen current, its immense gravitational influence subtly guiding the majestic swirl of hundreds of billions of stars and gas in the luminous disk. Modern cosmological simulations and extensive observations of galaxy formation across the universe strongly and consistently support the existence of these dark matter halos. Without them, it becomes incredibly challenging, almost impossible, to explain how large-scale structures like galaxies and vast galaxy clusters could have formed, evolved, and persisted in their observed forms throughout the universe's 13.8 billion-year history. The dark matter provides the initial gravitational seeds, the subtle primordial density fluctuations in the very early universe, around which ordinary matter could slowly coalesce under gravity's gentle pull, eventually forming the luminous galaxies and intricate cosmic web we observe today. It is a silent, pervasive, and fundamental force, operating on scales far beyond our immediate perception, yet fundamentally shaping the very cosmic landscape we inhabit, determining its structure and destiny. The sheer scale and subtle influence of this dark matter halo are truly difficult for the human mind to fully grasp. It extends far beyond the furthest globular clusters, potentially reaching up to 1 million light-years or more from the galactic center. This means that even as we consider ourselves residents of the Milky Way's vibrant disk, our true galactic home is enveloped within a much larger, mostly invisible entity, a vast gravitational well that extends deep into the intergalactic void, connecting our galaxy to the larger cosmic web. Our entire solar system, our beloved sun, and all the countless stars we perceive glittering in the night sky are, in a cosmic sense, merely tiny luminous specks nestled within this colossal unseen structure. It is a constant and humbling reminder of how much of the universe remains hidden from our direct view, silently influencing the visible world with its profound, enduring gravitational embrace. This understanding profoundly shifts our perspective on our place within the cosmos. We are not just floating in a bright, star-filled disk, a lone island of light in the darkness, but are intricately and inextricably woven into a far more extensive, dark, and ancient cosmic tapestry. The galactic halo, particularly its dominant dark matter component, stands as a testament to the universe's elegant complexity and its astonishing capacity for hidden depths, for structures that operate beyond our immediate senses. It is a truly profound thought that the very stability of our home galaxy, the continued existence of the Milky Way as a cohesive, spiraling entity, depends utterly on something we cannot see, cannot touch, and cannot directly detect with our current instruments. It is a universe of invisible forces and unseen structures, quietly dictating the grand cosmic ballet, a dance of gravity and mystery. And in this knowledge, in this quiet contemplation of the unseen, we find a tranquil wonder, a deeper, more expansive connection to the silent, majestic forces that govern our existence within the vastness, allowing our minds to drift into the quiet depths of the cosmos. Having quietly contemplated the vast, invisible embrace of our galaxy's dark matter halo, we might now allow our minds to drift even further outward, past the farthest globular clusters and the most distant wisps of gas, into the truly immense regions that lie beyond. The cosmic void. When we speak of the galactic halo, we describe a sphere of unseen mass that gravitationally anchors our Milky Way. Yet this halo, for all its colossal size, is itself merely a denser knot within an even grander, more expansive, and profoundly empty cosmic architecture. The term void often conjures images of absolute nothingness, a pure and perfect vacuum. However, in the universe, even what appears to be empty is rarely truly vacant. These cosmic voids, the largest structures in the universe, are not entirely devoid of matter, but rather represent regions where the density of matter is exceptionally low, orders of magnitude less than the average density of the cosmos. Instead of being perfectly empty, they are sparsely populated with stray atoms of hydrogen and helium, faint wisps of intergalactic gas, and perhaps the occasional isolated dwarf galaxy, like faint, lonely lanterns adrift in an endless, silent sea. These particles are incredibly diffuse, spread out over millions of light years, making the density within a void far less than that of the best vacuum we can create in any laboratory on Earth. Even then, on the quantum scale, the vacuum itself is never truly empty, constantly buzzing with virtual particles, flickering in and out of existence, a concept we have explored before. These colossal voids are not randomly scattered. Rather, they form part of what cosmologists refer to as the cosmic web, a breathtakingly intricate, sponge-like structure that defines the large-scale arrangement of matter in the universe. Imagine this web as a vast three-dimensional network, a kind of cosmic neural network where galaxies and galaxy clusters are concentrated in luminous filaments and nodes, while the spaces between these threads are the voids, vast bubbles of relative emptiness. Our Milky Way, along with its galactic neighbors in the local group, resides near the edge of a particularly large void known as the local void, a region millions of light years across, hinting at the universe's grand, structured emptiness that surrounds us. The formation of these titanic voids is a direct consequence of the interplay between gravity and dark energy over cosmic time. In the early universe, tiny quantum fluctuations in the distribution of matter, magnified by cosmic inflation, began to grow. Regions with slightly higher densities of dark matter exerted a stronger gravitational pull, slowly drawing in more and more surrounding matter. Conversely, regions with slightly lower densities gradually emptied out as matter migrated towards the denser, more attractive gravitational wells. This process, driven primarily by gravity, sculpted the initial cosmic web, pulling galaxies into clusters and superclusters and simultaneously carving out the immense, underdense regions we now observe as voids. As the universe continued its expansion, another force, dark energy, began to exert its dominance, particularly in the vast empty regions of space. While gravity works to pull matter together, dark energy acts as a repulsive force, accelerating the expansion of space itself. In the dense filaments and clusters, gravity still holds sway, binding galaxies together. However, within the voids, where matter is so sparse and gravity's influence is minimal, dark energy reigns supreme. It actively pushes these underdense regions apart, causing them to expand even faster than the average expansion rate of the universe. This accelerated expansion within the voids contributes to their remarkable emptiness, ensuring that any stray particles or galaxies within them are further distanced from one another, deepening their isolation and emphasizing their serene, silent growth. The study of these voids offers profound insights into the nature of dark energy, one of the most mysterious components of our universe. By observing how voids evolve and expand over cosmic epochs, astronomers can gather crucial data to refine our understanding of dark energy's properties and its ultimate influence on the fate of the cosmos. For instance, the rate at which voids grow provides a unique cosmological probe, acting as a cosmic laboratory to test different models of dark energy and even gravity itself. Scientists, using sophisticated simulations and observational data from vast sky surveys, are mapping these voids, treating them not as mere empty spaces, but as active, evolving components of the universe's grand design, silent witnesses to its accelerating expansion. Our own galaxy, the Milky Way, is not stationary within this cosmic web. We are moving, gently yet inexorably, influenced by the gravitational pulls of nearby clusters and the subtle push of expanding voids. Our local group, along with thousands of other galaxies, is being drawn towards a massive concentration of matter known as the Great Attractor, while simultaneously being influenced by the expansion of the local void. This complex dance illustrates that even within the seemingly stable framework of the galactic halo, we are part of a larger, dynamic, and constantly evolving cosmic ballet. To truly comprehend the universe, then, we must look beyond the gleaming lights of galaxies and stars and acknowledge the profound significance of the immense, dark, and mostly empty spaces that separate and define them. These voids, these vast regions of cosmic calm, are not merely blank canvases. They are active participants in the universe's grand narrative, silently expanding, shaping the cosmic web, and offering deep clues to the fundamental forces that govern all of existence. And as we consider our own small, luminous presence within this structured emptiness, we might reflect on the intricate balance between matter and void, between the seen and the unseen, finding a quiet reverence for the universe's elegant, understated grandeur. We are, in a profound sense, creatures of the cosmic web, intricately connected to both its luminous knots and its expansive, tranquil voids. As our gaze extends beyond the serene, albeit invisible expanse of the Milky Way's dark matter halo, we begin to perceive a different kind of cosmic interaction, one that intimately connects our galaxy to its immediate surroundings, and in turn, shapes its very destiny. Within this vast halo, and sometimes venturing beyond it, a retinue of smaller galaxies dances a complex gravitational ballet around our own. These are the satellite galaxies, silent companions, often dwarf galaxies, that are gravitationally bound to the Milky Way, forever caught in its immense gravitational embrace. Our galaxy is not a solitary island in the cosmic ocean. It possesses a family of these smaller systems, each a miniature galaxy in its own right, though often much dimmer and far less spectacular than the Milky Way's luminous disk. Perhaps the most famous of these are the Magellanic Clouds, the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as hazy patches of light. These two irregular dwarf galaxies are currently engaged in a slow, majestic orbit around the Milky Way, their gravitational interactions creating intricate stellar streams and influencing the very structure of our galaxy's outer reaches. Beyond these prominent companions, there are dozens of smaller, fainter dwarf spheroidal galaxies, so diffuse and dim that they are incredibly challenging to detect. These elusive systems, sometimes containing only a few thousand stars, are scattered throughout the galactic halo, each a tiny, ancient collection of stars, quietly tracing their paths through the dark matter that dominates their existence. The orbits of these satellite galaxies are far from simple planetary paths. Instead, they are complex, elongated trajectories, deeply influenced by the uneven, clumpy distribution of the dark matter halo. Scientists believe that the dark matter halo itself is not a perfectly smooth sphere, but contains numerous smaller concentrations, known as dark matter subhalos. These subhalos are like gravitational eddies within the larger current, and it is within these subhalos that many of the dwarf satellite galaxies are thought to reside. The interactions between these satellite galaxies and the Milky Way are not always gentle. As a smaller galaxy orbits, the immense gravitational pull of the Milky Way, particularly its dense central regions and the massive dark matter halo, exerts powerful tidal forces upon it. These forces can stretch and distort the satellite, pulling at its stars and gas, gradually stripping them away from their original galaxy and scattering them into vast, elongated streams that wrap around the Milky Way like cosmic ribbons. This process of gravitational stripping and absorption is often referred to as galactic cannibalism, though the term perhaps lends too much drama to what is, in fact, a natural and continuous process of galactic evolution. It is not a violent, sudden consumption, but a slow, inexorable weaving of one galaxy's components into the fabric of another. We observe direct evidence of this ongoing process in the form of stellar streams, long, thin trails of stars that were once part of dwarf galaxies but have now been gravitationally torn away and stretched across hundreds of thousands of light years in the Milky Way's halo. For example, the Sagittarius stream is a prominent example, the remnants of the Sagittarius dwarf's spheroidal galaxy, a small system that has been gradually unraveled by the Milky Way's tides over billions of years. Each star in these streams is a silent testament to a galaxy's slow, majestic demise and its contribution to the growth of a larger entity. These accretion events, the gradual absorption of smaller galaxies, play a crucial role in the growth and evolution of the Milky Way. Each absorbed dwarf galaxy contributes its stars, gas, and, significantly, its own share of dark matter to our galaxy. This continuous process of accretion builds up the Milky Way over cosmic time, adding new stellar populations to its halo and enriching its disk with fresh gas that can fuel new star formation. It is a slow, patient construction where the larger galaxy grows by incorporating the smaller ones, constantly reshaping its own gravitational landscape. The very size and mass of our Milky Way today are a result of billions of years of such interactions, a testament to its long history of gathering and integrating its smaller companions. Looking towards the distant future, these interactions are set to escalate on an even grander scale. Our Milky Way is on a collision course with its nearest galactic neighbor, the Andromeda Galaxy. In approximately 4.5 billion years, these two spiral behemoths, each enveloped in its own colossal dark matter halo and surrounded by its retinue of satellite galaxies, will begin their majestic gravitational dance, eventually merging to form a new, larger elliptical galaxy, sometimes playfully dubbed Milky Way. This future event, while sounding dramatic, will be a slow, drawn-out process of interweaving and transformation, a continuation of the same tidal forces and accretion processes we observe with our current satellite galaxies, but on an unimaginably grander stage. Stars will not collide, but their orbits will be profoundly altered, and the dark matter halos of both galaxies will merge, forming an even larger, more complex gravitational structure. This cosmic narrative of our galaxy's halo, populated by ancient stars and devoured dwarf galaxies, and its immersion within the grander cosmic web of voids and filaments, offers a profound sense of interconnectedness. We, on our small planet, orbiting a single star within the Milky Way's disk, are part of this continuous, silent cosmic evolution. Our galaxy is not a static entity, but a living, breathing system, constantly growing, interacting and transforming, guided by the unseen hand of dark matter and the expansive push of dark energy. To contemplate these vast dynamic structures, these slow, majestic dances of cosmic entities, is to truly appreciate the profound, intricate beauty of the universe and our own small yet significant place within its endless unfolding story, inviting a deep, tranquil understanding. Having journeyed through the unseen architecture of our Milky Way's dark matter halo and contemplated the slow, gravitational ballet of its satellite galaxies, we find ourselves at a fascinating juncture in cosmic time. The future of our own galaxy, as we briefly touched upon, involves a monumental encounter with the Andromeda Galaxy, culminating in the formation of a majestic new elliptical entity, often referred to as Milky Way, in approximately 4.5 billion years. This future galaxy will represent a new chapter in galactic evolution, a grander, more massive system, yet it too will exist within the intricate tapestry of the cosmic web, continuously interacting with the vast underdense regions that surround it. Milky, for all its future splendor, will still be a luminous node within a much larger, predominantly dark matter structure. Its immense gravitational potential will be enclosed within an even more expansive dark matter halo, an inherited legacy from both the Milky Way and Andromeda. This merged halo will continue to exert a powerful gravitational influence over any remaining smaller satellite galaxies or stray gas clouds in its vicinity, gradually incorporating them into its growing mass. The process of galactic accretion, of slow, gentle consumption and assimilation, will persist, ensuring that Milky, like its predecessors, remains a dynamic, evolving system, forever drawing in the cosmic material that drifts into its gravitational well. It will be a beacon of light, a supergalaxy, but its true dimensions and its profound stability will still be defined by the unseen, silent presence of its dark matter embrace, anchoring it within the grander cosmic architecture. But what of the voids that define the spaces between these grand galactic structures? As we previously discussed, these immense regions of relative emptiness are not static. They are actively expanding, driven by the enigmatic force of dark energy. In the eons following the formation of Milky, these cosmic voids will continue their inexorable growth, becoming ever larger, ever emptier, and ever more dominant in the universe's large-scale structure. The filaments and nodes of the cosmic web, where galaxies like Milky reside, will become increasingly isolated, separated by ever-widening gulfs of expanding void. Imagine the intricate veins on a leaf slowly receding, leaving behind larger and larger spaces of translucent emptiness. This is a gentle analogy for the cosmic web's future. This relentless expansion of the voids will have profound implications for the observable universe of the far future. Galaxies that are currently within our observable horizon, visible as faint smudges of light, will eventually be carried away by the accelerating expansion of space itself, receding beyond the reach of light, eventually disappearing from our view entirely. Milky, along with its immediate gravitational neighbors, will become an isolated island of light, a solitary beacon in an increasingly vast and dark cosmos. The light from distant galaxies, once a constant source of wonder and scientific inquiry, will no longer reach us, leaving future inhabitants of Milky to gaze upon an almost entirely empty night sky. This is not a sudden, dramatic disappearance, but a slow, gradual fade, a tranquil dimming of the cosmic lights over incomprehensibly long time scales, a silent testament to the enduring power of dark energy. The nature of these voids, these regions of profound cosmic calm, also prompts us to reflect on the very concept of emptiness. Is a void truly nothing? As we explored, even in the most rarefied corners of space, quantum mechanics dictates a constant, ephemeral dance of virtual particles, flickering into existence and vanishing again. So, while the cosmic voids are largely devoid of visible matter, they are far from being inert or truly empty. They are fields of potential, regions where the subtle energies of dark energy are most pronounced, quietly shaping the universe's destiny. They represent a kind of profound, active silence, a canvas upon which the universe's grandest forces are at play, pushing matter apart and defining the boundaries of existence. This subtle activity, this underlying hum of quantum foam and dark energy, ensures that even the most desolate cosmic expanse is imbued with a quiet, persistent vitality, a constant, gentle motion. How do we, as fleeting consciousnesses within this vast cosmic tapestry, seek to understand these immense empty spaces? Our current observational tools, powerful as they are, primarily detect light, focusing our attention on the luminous threads of the cosmic web. Yet, new frontiers in astronomy are emerging, allowing us to probe the voids more directly. Studies of the cosmic microwave background radiation, the faint afterglow of the Big Bang, reveal subtle imprints left by the voids as they grew, like faint ripples on an ancient pond. Furthermore, The gravitational lensing of light from distant galaxies as it passes through the tenuous matter within voids provides another indirect yet powerful means of mapping their distribution and understanding their gravitational influence. Future generations of telescopes, perhaps observing in new wavelengths or utilizing novel detection techniques, will undoubtedly continue to peel back the layers of this cosmic mystery, revealing an even more intricate and astonishing picture of the universe's large-scale structure. Ultimately, the contemplation of the galactic halo and the cosmic void invites a profound reflection on our own existence. We are part of a galaxy that is itself a luminous island within a sea of dark matter, floating within a larger, mostly empty, yet dynamically structured universe. Our very stability, our ability to exist and ponder these questions, is a direct consequence of these invisible forces and grand cosmic architectures. It is a reminder that even in the vast silent stretches of the cosmos, there is a deep underlying order, an elegant interplay of forces that shapes everything from the smallest subatomic particle to the largest supercluster of galaxies. And in this realization, in this quiet acceptance of our place within such a majestic and mysterious unfolding, we can find a profound sense of peace, allowing our thoughts to drift gently into the tranquil depths of sleep, carried by the silent currents of the cosmos. Having traversed the serene, dark matter halo of our Milky Way and contemplated its slow gravitational merging with Andromeda, shaping the future Milkomeda, we now arrive at an even grander, more profound aspect of the cosmic tapestry, the ultimate fate of these vast structures within an ever-expanding universe dominated by the cosmic void. Our journey has revealed that the visible galaxies, including our future Milkomeda, are merely luminous islands within an ocean of unseen dark matter, themselves embedded within an even larger, sponge-like network of filaments and immense, underdense voids. The relentless expansion of these voids, driven by dark energy, leads to a future where these luminous islands become increasingly isolated, profoundly altering the very nature of our observable cosmos. As cosmic time progresses, the accelerating expansion of the universe, propelled by dark energy, will cause all but the most gravitationally bound structures to recede from one another at an ever-increasing pace. Galaxies that are currently visible to us, even those in distant clusters, will eventually cross a boundary known as the cosmological event horizon. This is not a physical barrier in space, but rather a limit to what we can ever observe. Once a galaxy crosses this horizon, the space between it and us expands faster than light can travel across it. Consequently, any light emitted by those galaxies will never reach us, rendering them permanently invisible, effectively disappearing from our observable universe. Milkomeda, in its far future isolation, will gaze upon an increasingly empty night sky, stripped of the grand tapestry of distant galaxies we marvel at today. This is not a dramatic, sudden vanishing, but a slow, inexorable fading, timescales so vast they defy human comprehension. Implications of this cosmic isolation for any future civilizations within Milkomeda are deeply contemplative. Their observable universe would shrink to encompass only the stars within Milkomeda itself, perhaps a few lingering satellite galaxies, and the ghosts of once visible neighbors. The vast cosmological context that we currently possess, the ability to study distant galaxies, to trace the evolution of the cosmic web, and to infer the conditions of the early universe from the cosmic microwave background, would be lost to them. They would inhabit a lonely island universe, unable to perceive the grander structure, the filaments, and the voids that define the universe on the largest scales. This loss of cosmic perspective would fundamentally alter their understanding of existence, reducing the universe to a single, isolated galactic entity, surrounded by an impenetrable, expanding darkness. It underscores the preciousness of our current epoch, a unique window in cosmic time when the universe is sufficiently old for complex structures to have formed, yet still young enough for us to observe its vast, intricate, and interconnected expanse. In this distant future, the cosmic voids will truly become the dominant architectural feature of the universe. They will continue to expand, merging with one another, creating ever larger regions of profound emptiness. The already sparse matter within them will become even more diluted, further reducing the chances of any gravitational interaction or the formation of new structures. These voids are not just passive empty spaces. They are active regions where dark energy exerts its most profound influence, shaping the overall geometry and destiny of the cosmos. They represent a kind of ultimate cosmic calm, a vast, silent expanse where the fundamental forces of the universe play out on scales beyond our current grasp, defining the very fabric of expanding space-time. The precise timeline and severity of this cosmic isolation depend critically on the fundamental nature of dark energy, which remains one of the most profound mysteries in modern physics. Is dark energy a constant and immutable property of space-time, as suggested by Einstein's cosmological constant? Or is it a dynamic, evolving field, sometimes referred to as quintessence, whose properties might change over time? The answers to these questions will dictate whether the universe continues to expand indefinitely, leading to the heat-death scenario where everything becomes cold, dark, and infinitely dilute, or if it might eventually lead to a big rip, where dark energy becomes so powerful that it tears apart even atoms. Scientists continue to study the expansion of the universe, diligently observing distant supernovae and mapping the distribution of galaxies and voids, seeking the subtle clues that will reveal dark energy's true identity. The voids themselves, as regions where dark energy's repulsive force is least opposed by gravity, act as sensitive probes, offering invaluable insights into this cosmic enigma. To reflect upon this distant future, where our luminous galactic home becomes a solitary beacon in an ever-darkening, expanding void, is to gain a deeper appreciation for the fleeting, vibrant richness of our present moment. We are privileged to inhabit a universe teeming with light, with galaxies stretching across billions of light-years, offering us a panoramic view of cosmic history. Our consciousness, our ability to ponder these grand questions of galactic halos and expanding voids, is a momentary flicker of awareness within this vast, unfolding narrative. It is a profound realization that the beauty and complexity of the universe are not eternal in their current manifestation, but are part of a grand, dynamic process of evolution and transformation. And in this tranquil contemplation, in this gentle acceptance of the universe's serene yet inexorable journey, we can find a quiet sense of wonder, allowing our minds to drift into a peaceful slumber, cradled by the vastness and mystery of the cosmos. Having drifted through the profound future of Milky Way and the ever-expanding cosmic voids, we are left with a deep sense of the universe's grand, silent architectures. Yet much of what we have discussed remains largely unseen, inferred rather than directly observed. This brings us to the fascinating challenge that astronomers and physicists constantly face. How do we truly map and understand these hidden realms, the galactic halo and the immense voids, when they interact so subtly with the light our telescopes detect? The quest to unveil these invisible structures is a testament to human ingenuity, pushing the boundaries of our observational capabilities and our theoretical understanding. Our primary method for probing the dark matter halo, for instance, relies heavily on the meticulous study of stellar kinematics. We cannot directly see dark matter, but we can observe its gravitational pull. By carefully measuring the speeds at which stars, globular clusters, and gas clouds orbit within the Milky Way, particularly at its outer edges and above and below its disk, scientists can infer the distribution of the unseen mass that must be present to keep these objects gravitationally bound. If there were only visible matter, these objects would move too slowly in the inner regions and too quickly in the outer regions to maintain their orbits. They would simply fly apart. The observed rotation curves of galaxies, which remain surprisingly flat even far from the luminous center, provide compelling evidence for a vast, extended halo of dark matter, shaping the gravitational landscape in ways that visible matter alone cannot. This method allows us to effectively weigh the invisible, mapping its pervasive influence through the movements of the luminous elements it cradles. Beyond individual stellar motions, another powerful technique for detecting the elusive presence of dark matter, both within galactic halos and in the larger cosmic web, is gravitational lensing. This phenomenon, predicted by Albert Einstein's theory of general relativity, occurs when the path of light from a distant background galaxy is bent by the gravitational field of a massive foreground object, such as a galaxy or an entire cluster of galaxies. The effect can magnify, distort, or even create multiple images of the background source. By analyzing the precise patterns of these distortions, astronomers can calculate the total mass of the foreground object, including its dark matter component. This lensing effect acts like a cosmic magnifying glass, allowing us to map the distribution of mass, both visible and dark, in regions that would otherwise remain opaque to our understanding. It provides a unique, independent confirmation of dark matter's pervasive influence, painting a picture of vast, invisible structures that subtly warp the very fabric of space-time around them. The galactic halo is not entirely dark, however. While dominated by dark matter, it also contains a significant amount of diffuse baryonic matter, ordinary matter composed of protons and neutrons in the form of extremely hot, tenuous gas. This gas, heated to millions of degrees Celsius during the galaxy's formation and subsequent accretion events, emits faint X-rays, which can be detected by specialized space telescopes. The presence of this hot gas is crucial because it helps to address what is known as the missing baryon problem. Cosmological models predict that there should be more ordinary matter in the universe than we can account for by summing up all the stars and gas in galaxies. Much of this missing baryonic matter is now believed to reside in these hot, diffuse halos surrounding galaxies and within the filaments of the cosmic web, acting as a kind of intergalactic fog. Studying this hot gas, its temperature, density, and distribution provides vital clues about the formation history of galaxies and the ongoing processes of accretion and outflow from the galactic disk, slowly unveiling the full baryonic picture of our galaxy's immense envelope. When we turn our attention to the cosmic voids, the challenge of observation becomes even more pronounced due to their extreme emptiness. Yet, even these vast regions leave their subtle fingerprints on the universe. The most ancient light we can detect, the cosmic microwave background radiation, carries tiny temperature fluctuations that are thought to be the seeds of all large-scale structure. As this ancient light traveled through the expanding universe, it passed through the gravitational potentials of growing voids and denser filaments. The integrated Sachs-Wolf effect, for example, describes how the energy of these photons changes as they traverse regions of varying gravitational potential, leaving subtle imprints on the cosmic microwave background map. By analyzing these minute patterns, cosmologists can infer the presence and evolution of voids, effectively mapping the universe's largest empty spaces from observations of its very first light. Furthermore, large-scale galaxy redshift surveys, which map the three-dimensional distribution of hundreds of thousands, even millions of galaxies, allow us to directly observe the boundaries of these voids. While the voids themselves are sparsely populated, the galaxies tend to congregate in the surrounding filaments and walls of the cosmic web, forming a luminous outline of the void shape. These surveys, like the Sloan Digital Sky Survey or the Dark Energy Survey, create intricate maps of the universe, revealing the vast bubble-like structures of voids nestled between the galaxy-rich filaments. By studying the sizes, shapes, and evolution of these voids, scientists gain crucial insights into the properties of dark energy, as its repulsive force is most evident in these underdense regions, influencing their expansion and growth over cosmic time. The future promises even more sophisticated tools to penetrate these dark and empty realms. Next-generation telescopes, such as the Square Kilometer Array, will be capable of detecting extremely faint radio emissions from neutral hydrogen gas, which is expected to exist in trace amounts even within voids, offering a direct probe of their elusive baryonic content. Missions like the Euclid satellite and the Nancy Grace Roman Space Telescope will provide unprecedented maps of gravitational lensing effects, allowing for even more precise measurements of dark matter distribution in halos and the overall cosmic web. Moreover, the ongoing search for dark matter particles in underground laboratories around the globe, though yet to yield a direct detection, represents a fundamental experimental effort to unveil the precise nature of this invisible substance that so profoundly shapes our galactic home and the universe beyond. Our journey through the galactic halo and the cosmic void is a continuous unfolding of knowledge, a testament to the universe's enduring mysteries and our persistent drive to comprehend them. Each new observation, each refined theory, brings us a little closer to understanding the hidden forces and structures that govern our existence. And in this endless pursuit, in this quiet contemplation of the known and the unknown, we find a tranquil sense of connection to the vast, majestic cosmos, a profound awareness of our place within its intricate, silent dance. Having quietly considered the remarkable ingenuity involved in mapping the invisible structures of the galactic halo and the immense cosmic voids, we now turn our thoughts to what these vast, silent observations truly reveal about the fundamental architecture of our universe. The data we gather from stellar kinematics, gravitational lensing, and the faint whispers of X-ray gas all coalesce into a profound understanding that the existence and evolution of galaxies like our Milky Way are inextricably linked to the unseen, particularly the pervasive influence of dark matter and the expansive nature of cosmic voids. These hidden realms are not merely passive backdrops, but active participants in the grand cosmic design, fundamentally shaping the luminous universe we perceive. At the very heart of galactic existence lies the dark matter halo, serving as the primordial gravitational cradle for all visible matter. In the universe's infancy, the ordinary baryonic matter, the protons, neutrons, and electrons that make up stars, planets, and ourselves, was too hot and too energetic to coalesce quickly under its own gravity. The universe was expanding rapidly, threatening to dilute any nascent clumps of matter before they could grow significant. It was the dark matter, immune to electromagnetic forces and therefore able to cool and clump much earlier, that provided the crucial gravitational scaffolding. These early concentrations of dark matter acted like cosmic anchors, drawing in the surrounding baryonic gas, giving it the necessary gravitational embrace to overcome the universe's expansion and begin the slow process of collapse. Without these dark matter halos, the intricate spiral beauty of galaxies like our own would likely never have formed, leaving the universe a far emptier, less structured place. It is a silent, fundamental partnership where the unseen provides the foundation for the seen, a delicate balance that allows for cosmic complexity. Within this dark matter framework, the baryonic component of the halo plays its own dynamic role. The hot, diffuse gas residing within the halo is not merely a static reservoir. It represents a continuous cycle of galactic respiration. Gas from the intergalactic medium, enriched by supernova explosions from earlier generations of stars, is constantly flowing into the halo, slowly cooling and eventually raining down onto the galactic disk. This inflow of fresh, cold gas provides the essential fuel for ongoing star formation in the Milky Way's vibrant arms. Conversely, powerful stellar winds and supernova explosions in the disk can drive outflows of gas back into the halo, enriching it with heavier elements and influencing the larger galactic environment. This constant ebb and flow, this gentle exchange of matter between the luminous disk and its expansive halo, illustrates a dynamic equilibrium, a slow, majestic breathing of the galaxy, ensuring its sustained vitality and continuous evolution over billions of years. And then there are the cosmic voids, those colossal regions of underdensity that seem, at first glance, to be mere empty spaces. However, their role in shaping the cosmic web is far more active and profound. Imagine them not as passive holes, but as expanding bubbles within the cosmic foam, actively pushing matter away from their centers and towards their edges. This repulsive effect, primarily driven by dark energy, accentuates the density contrasts in the universe. Matter that falls into the gravitational wells of dark matter halos then congregates into the luminous filaments and nodes of the cosmic web, while the voids themselves grow larger, becoming ever more pristine in their emptiness. The voids thus define the very boundaries of galactic structures, acting as the negative space that sculpts the positive. They are the silent architects of the universe's grandest designs, ensuring that matter is not uniformly distributed, but organized into the intricate, interconnected network we observe. The harmonious interplay between dark matter, baryonic matter, and these expansive voids is a testament to the universe's elegant self-organization. The dark matter halos provide the initial gravitational seeds, the baryonic matter fuels the luminous activity of galaxies, and the voids, expanding under the influence of dark energy, carve out the vast cosmic architecture, pushing matter into the filaments where galaxies cluster. This intricate dance of invisible forces and visible light creates the conditions necessary for complex structures to form, evolve, and persist over cosmological timescales. It is a finely tuned cosmic symphony where each component, whether seen or unseen, plays an indispensable part in the universe's grand unfolding. Reflecting on this profound interdependence, we might consider our own place within this cosmic ballet. Our very existence, our ability to think, to question, to marvel at the universe's intricate workings, is a direct consequence of this delicate cosmic balance. The atoms in our bodies, forged in the hearts of ancient stars, were drawn together by the gravitational embrace of a dark matter halo, eventually settling into the luminous disk of our galaxy. We are, in a very literal sense, products of this grand cosmic architecture, beneficiaries of the unseen forces that shape the universe. And in this tranquil realization, in this quiet acceptance of our deep connection to the vast, evolving cosmos, minds to drift into a serene and knowledgeable sleep. Our profound understanding of the universe's grand architecture as we've explored is undeniably shaped by the invisible. And among these unseen influences, dark matter stands as perhaps the most enigmatic and fundamental. We have inferred its pervasive gravitational embrace within the galactic halo, and its crucial role in sculpting the cosmic web, yet its true nature remains one of the deepest mysteries in modern physics. What exactly is this invisible substance that outweighs all the visible matter in the universe by a factor of more than 5 to 1? This question guides an extraordinary scientific quest, a global endeavor to unveil a fundamental component of reality that interacts with us only through the subtle bending of space-time itself. Scientists believe that dark matter is not merely ordinary matter that happens to be dark, like unlit gas clouds or faint planets. Instead, it is thought to be composed of an entirely new class of elementary particles, particles that do not interact with light or other electromagnetic forces. If it were ordinary matter, even if dark, we would expect to detect some form of interaction, some faint emission or absorption, or at least a different distribution than what we observe. Its distinct behavior suggests a realm of physics beyond our current standard model of particles and forces, beckoning us towards a deeper understanding of the universe's fundamental constituents. This search is not just about finding a new particle, it is about rewriting our most fundamental theories. Several theoretical candidates have emerged from the quiet contemplation of physicists. One prominent contender is the weakly interacting massive particle, or WIMP. As the name suggests, WIMPs would be particles with significant mass, but they would interact only very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. Imagine a gentle, pervasive cosmic wind composed of these particles, flowing through the Earth and even through our bodies, without our ever feeling its subtle touch. Another intriguing possibility is the axion, a much lighter particle originally proposed to solve a different problem in quantum chromodynamics, but which could also account for dark matter if it possesses the right mass and interaction strength. These particles would be even more elusive, like silent ethereal waves permeating the cosmos. The universe in its vastness might hold an entire zoo of such exotic, unseen inhabitants. The quest to detect these elusive particles is being pursued through a variety of ingenious experimental approaches, each designed to capture the faintest whisper of dark matter's presence. Direct detection experiments, often located deep underground in former mines or mountain tunnels, aim to shield detectors from cosmic rays and other background noise. Here, ultra-sensitive detectors, cooled to near absolute zero, wait patiently for a rare collision between a dark matter particle and an atomic nucleus within the detector material. It would be an incredibly subtle event, perhaps causing a tiny recoil or a flash of light, but one that could definitively confirm dark matter's existence. Think of it as listening for a single raindrop in a vast subterranean silence. Indirect detection experiments, on the other hand, search for the byproducts of dark matter particles annihilating or decaying in space. If dark matter particles were to collide with one another in dense regions, such as the galactic center or dwarf galaxies, they might produce observable particles like gamma rays or neutrinos. Space telescopes and ground-based observatories meticulously scan the cosmos for these faint, telltale signatures, hoping to catch a glimpse of dark matter's destructive yet informative interactions. It's like trying to find evidence of a secret conversation by listening for its echoes. Furthermore, particle accelerators, such as the Large Hadron Collider at CERN, are also playing a role. By smashing ordinary particles together at incredibly high energies, physicists hope to recreate the conditions of the early universe, potentially generating dark matter particles that could then be detected. While no definitive dark matter particle has yet been discovered, the ongoing search continues to refine our understanding of fundamental particle physics, narrowing down the possibilities and guiding future experiments. Each null result, each non-detection, provides valuable information, slowly painting a clearer picture of what dark matter is not, bringing us closer to understanding what it is. The profound implications of finally identifying dark matter extend far beyond astrophysics. It would fundamentally reshape our understanding of matter itself, requiring an expansion of the standard model of particle physics and potentially opening doors to entirely new physical laws and dimensions. It would be a monumental discovery, comparable to the realization that atoms are made of smaller particles, or that gravity warps space-time. It would reveal a deeper, more intricate layer of reality, a silent, invisible foundation upon which the luminous universe rests. As we lie here, contemplating these profound scientific pursuits, we might reflect on the humility inherent in this quest. For all our advanced technology and intellectual prowess, the universe still holds vast secrets, with much of its fundamental composition remaining hidden from our direct perception. The dark matter halo, this invisible embrace, and the cosmic voids, these expanding realms of quiet energy, remind us that our understanding is always evolving, always deepening. We are continually learning to see beyond the obvious, to listen for the whispers of the unseen, and to embrace the quiet grandeur of a cosmos that is far more mysterious and magnificent than we can often imagine. And in this acceptance of mystery, in this tranquil wonder, we can find a profound sense of calm, allowing our minds to drift into the peaceful unknown. Has illuminated a universe far more intricate and mysterious than meets the eye, revealing that the luminous tapestry of stars and galaxies is but a small fraction of the grand cosmic whole. The persistent enigmas of dark matter and dark energy, which sculpt our galaxy's unseen embrace and propel the expansion of the voids, challenge our most fundamental theories of physics. This profound incompleteness in our understanding is not a failure, but rather an invitation, a quiet beckoning towards new frontiers of knowledge, suggesting that the universe holds deeper, more subtle layers of reality yet to be unveiled. The Standard Model of Particle Physics, our most successful framework for describing the fundamental particles and forces that govern the visible universe, simply does not account for dark matter or dark energy. This means that more than 95% of the cosmos operates under principles that remain outside our current theoretical grasp. Imagine trying to understand a vast symphony while only being able to hear a few of the instruments. This profound realization inspires both humility and an intense drive for discovery. It implies that there are new particles, new forces, or even entirely new dimensions of reality that profoundly influence our existence, yet remain hidden from our direct sensory experience. The universe, in its quiet wisdom, reveals its secrets slowly, patiently. This fundamental gap in our knowledge has led scientists to explore various theoretical avenues, pushing the boundaries of human thought. While the leading candidates for dark matter remain exotic particles like WIMPs or axions, the absence of their direct detection has also spurred a resurgence of interest in alternative gravitational theories. These theories, sometimes referred to as modified Newtonian dynamics, or MUND, propose that gravity itself behaves differently on galactic scales than it does on the smaller scales we observe in our solar system. Instead of postulating invisible dark matter, MUND suggests that Newton's and Einstein's laws of gravity need a subtle modification when gravitational accelerations become very small, as they do in the outer regions of galaxies. This scientific debate between the existence of new particles, dark matter, and the modification of fundamental laws, MUND, is a vibrant and essential part of the scientific process. It demonstrates the healthy skepticism and rigorous testing that define our pursuit of truth. Currently, the overwhelming body of cosmological evidence, particularly from observations of the cosmic microwave background, large-scale structure formation, and gravitational lensing in galaxy clusters, strongly favors the dark matter hypothesis. However, the continued exploration of alternative theories ensures that our understanding remains robust, constantly challenged, and open to new interpretations, preventing complacency and fostering intellectual growth. It is a slow, thoughtful dance between observation and theory, each refining the other in a continuous cycle of discovery. The very existence of these grand, invisible structures, the galactic halo and the cosmic voids, prompts us to reconsider our perception of reality itself. We tend to focus on the tangible, the luminous, the aspects of the universe that are immediately accessible to our senses and instruments. Yet the cosmos reveals that the majority of its influence, its gravitational scaffolding, and its expansive growth stem from realms that are inherently dark, silent, and elusive. This is a profound lesson in perspective, that the universe is far more than what we can see or touch, and that its deepest truths often lie hidden in plain sight, woven into the very fabric of space-time. Consider the notion that our entire visible universe is akin to the delicate foam on a vast, dark ocean. The foam, with its intricate patterns and shimmering beauty, is what we perceive directly. But the true depth, the immense volume, and the powerful currents that govern its existence are all beneath the surface, unseen. The dark matter halo and the cosmic voids represent this hidden ocean, silently dictating the ebb and flow of galaxies, shaping the destiny of the universe. This perspective, far from diminishing our place in the cosmos, imbues it with a deeper significance. We are not merely inhabitants of a small, luminous corner, but conscious observers capable of inferring and contemplating these grand, unseen forces, becoming, in a sense, the universe's own awareness of its hidden depths. The ongoing quest to understand dark matter and dark energy, to fully map the galactic halo and the cosmic voids, is a testament to the enduring human spirit of inquiry. It is a journey into the unknown, driven by curiosity and a deep desire to comprehend the fundamental nature of our existence. Each incremental step, each new piece of data, each refined theory brings us closer to a more complete and coherent picture of the cosmos. And in this tranquil pursuit, in this quiet contemplation of the universe's most profound mysteries, we find a deep sense of wonder and connection, allowing our minds to drift peacefully into the quiet depths of the cosmos, embracing the unseen, expanding the very lexicon of cosmic understanding, each offering a glimpse into potential new physics, an ethereal presence woven into the very fabric of our immediate reality, their existence a testament to the universe's capacity for hidden depths, each playing a role in its silent, majestic orchestration, meticulously creating a sanctuary of silence for scientific inquiry, almost imperceptible, a single, profound signal emerging from the cosmic quietude, a testament to our profound dedication, the halos of high energy like deciphering ancient cosmic hieroglyphs, a subtle imprint on the grand cosmic canvas. Crucial role in this grand quest. Extreme directly or indirectly in these powerful machines, meticulously with increasing precision, but surely a methodical and patient unfolding of cosmic truth, touching upon the very foundations of our scientific worldview, a significant forces and even hidden dimensions of reality. It would be a monumental discovery, comparable in its impact, constituent particles, or that gravity warps the very fabric of space-time. Such a revelation would unveil, challenging our anthropocentric perceptions of the cosmos and our place within it. That cradles our galaxy, that sculpts the largest structures, that permeates the unknown, depths of the cosmic unknown, a serene and gentle descent into slumber. And the ongoing quest for dark matter, we now turn our thoughts to an even more perplexing and powerful constituent of our universe, dark energy. If dark matter provides the unseen gravitational glue that holds galaxies together, dark energy acts as a cosmic anti-gravity, silently yet inexorably pushing the very fabric of space apart, particularly evident in the vast underdense regions we call voids. Its unexpected discovery, less than 3 decades ago, fundamentally reshaped our understanding of the universe's destiny, introducing a new, profound mystery into the very heart of modern cosmology, a riddle that continues to challenge our deepest scientific intuitions and theoretical frameworks. The story of dark energy began its profound unfolding in the late 1990s, when 2 independent teams of astronomers, working diligently and with meticulous precision, led by pioneering scientists such as Saul Perlmutter, Brian Schmidt, and Adam Rees, were meticulously observing distant Type Ia supernovae. These particular stellar explosions, born from the dramatic demise of white dwarf stars in binary systems, are known for their consistent and predictable peak luminosities, functioning as highly reliable standard candles across the immense stretches of cosmic distances. This unique characteristic allows astronomers to accurately measure how far away these supernovae are from us, and crucially, to infer how fast the universe was expanding at different points in its extensive history. The prevailing scientific expectation, rooted deeply in the models of a universe born from the Big Bang, was that its expansion should be gradually slowing down, decelerating under the collective gravitational pull exerted by all the matter within it. However, the meticulous data gathered from these distant supernovae told a startlingly different and deeply counterintuitive tale. To the profound astonishment of the entire scientific community, the light from these distant stellar beacons appeared significantly dimmer than theoretical predictions suggested, indicating that they were, in fact, considerably farther away than would be expected in a universe that was merely decelerating. This profound observational discrepancy led to an inescapable and revolutionary conclusion. The expansion of the universe is not slowing down. It is, with an almost silent, yet undeniable force, accelerating. Something entirely unknown, something with a pervasive, repulsive gravitational effect, was actively pushing the very fabric of space apart, causing it to stretch faster and faster over vast cosmic timescales. This mysterious, unseen force, fundamentally altering the cosmic narrative, was given the evocative and now familiar name, dark energy. Unlike dark matter, which is characterized primarily by its gravitational attraction and its essential role in binding structures like galaxies and clusters together, dark energy is fundamentally defined by its pervasive gravitational repulsion. It is not something that clumps together to form halos or filaments. Instead, current theoretical models suggest it is a uniform energy density inherent to space itself, an intrinsic property of the vacuum that permeates every corner of the cosmos. As space expands, more space is continuously created, and with it, more dark energy comes into existence, leading to an ever-increasing and accelerating expansion. The leading theoretical candidate for dark energy is a concept that echoes back to the early days of cosmology, a reintroduction of Albert Einstein's famous cosmological constant. This term, originally a somewhat arbitrary addition to his groundbreaking equations of general relativity, was initially included to mathematically achieve a static universe, before Edwin Hubble's revolutionary observations definitively confirmed the universe's expansion. Einstein famously later referred to it as his biggest blunder. Yet now, with the discovery of accelerating expansion, it appears that a cosmological constant, representing the intrinsic energy of the vacuum, might indeed be the simplest and most elegant explanation for dark energy. However, a profound challenge persists. The observed value of this vacuum energy is astonishingly, almost incomprehensibly, small when compared to theoretical predictions derived from quantum field theory. This monumental discrepancy, spanning an astounding 120 orders of magnitude, represents one of the most profound and persistent unsolved problems in all of physics. This cosmic riddle, this vast gulf between our most advanced theories and the empirical reality we observe, highlights the deep intellectual challenges that still lie at the very frontier of our understanding. A silent call for a new paradigm. The pervasive presence of dark energy profoundly influences the cosmic voids we discussed earlier, acting as a cosmic sculptor on the grandest scales. In the denser regions of the cosmic web, the intricate filaments and massive clusters where galaxies congregate in luminous grandeur, gravity still largely dominates, managing to overcome the repulsive push of dark energy to bind matter together into cohesive structures. However, within the vast, underdense expanse of the voids, those immense bubbles of relative emptiness where ordinary matter is exceptionally sparse and gravity's influence is at its absolute minimum, dark energy reigns supreme and unopposed. Here, its repulsive force is largely unchecked, actively pushing these regions apart with an ever-increasing vigor, universe's average expansion rate. The voids, therefore, are not merely passive empty spaces or voids of nothingness. They are, in essence, the dynamic battlegrounds where dark energy's influence is most acutely felt and observed, acting as colossal cosmic laboratories for studying its enigmatic properties. Their accelerated growth, their increasing emptiness, and their very definition within the cosmic web are direct manifestations of dark energy's relentless and pervasive expansion, quietly sculpting the large-scale structure of the cosmos with an invisible, yet undeniably powerful, hand, shaping the future of all that exists. To unravel the mysteries of dark energy and constrain its true nature, scientists employ a sophisticated suite of diverse observational techniques, each contributing a vital piece to this immense cosmic puzzle. Beyond the groundbreaking Type Ia supernova that first revealed its presence, astronomers meticulously map the large-scale distribution of galaxies across vast swathes of the sky, observing with painstaking detail how they cluster and, crucially, how the expansive voids between them grow and evolve over immense cosmic time. This technique, known as baryon acoustic oscillations, utilizes the faint characteristic imprints of primordial sound waves that propagated through the early universe as a kind of cosmic standard ruler to precisely measure distances and the universe's expansion rate at different epochs. Gravitational lensing, both in its strong and weak forms, also provides invaluable data by revealing how dark energy subtly influences the growth of large-scale structure and the bending of light from distant sources, offering an independent verification of its effects. By combining these diverse and complementary observational probes, utilizing the most powerful telescopes and advanced analytical methods, scientists are slowly but surely piecing together a clearer, more coherent picture of dark energy's behavior, seeking to determine if it is truly a constant, immutable force intrinsic to space, or if its properties might dynamically change over the universe's immense and unfolding lifespan. The ultimate implications of dark energy are nothing short of staggering, for its nature will define the long-term, ultimate fate of the entire cosmos. If dark energy remains constant, an enduring property of space itself, or if it continues to strengthen over cosmic time, the universe will proceed to expand at an ever-accelerating rate, leading inevitably to an increasingly cold, dark, and empty future. Galaxies will eventually become truly isolated islands of light, separated by unfathomable distances of expanding void, their light unable to reach one another. Stars within these galaxies will eventually burn out, exhausting their nuclear fuel, and even black holes will eventually evaporate through a process known as Hawking radiation, leaving behind a universe of ultimate desolation. In the most extreme scenario, a big rip, dark energy could become so overwhelmingly powerful that it would overcome all fundamental forces, tearing apart even atoms themselves, leaving behind a universe of unbound fundamental particles, drifting into an eternal, silent slumber. Such a grand, inexorable unfolding is a powerful reminder of the ephemeral and transient nature of all structure and life within the vastness of space, a cosmic narrative of transformation. And as we contemplate these ultimate cosmic destinies, these profound possibilities for the universe's future, all intricately guided by the unseen hand of dark energy, we are reminded of the profound beauty and inherent fragility of our own precious moment in time. We are privileged to inhabit an epoch when the universe is vibrant, filled with the scattered light of countless galaxies and teeming with complexity, a brief luminous window in cosmic history before the ultimate triumph of the void. This awareness, far from being unsettling, can evoke a deep sense of wonder and a quiet, profound appreciation for the universe's dynamic and awe-inspiring journey, a testament to its endless capacity for mystery and transformation. We are here now to witness and to humbly attempt to understand these grand, silent processes, to be, and its ultimate fate. And with this tranquil understanding, with this peaceful acceptance of the cosmos's vast and gentle rhythm, we can allow our thoughts to gently dissolve, drifting into the quiet, expansive embrace itself, urging us to look deeper, to listen more closely to its silent pronouncements. Elegant yet challenging, Idea offers a different lens through which to view the cosmic puzzle, reminding us that even our most cherished physical laws might be approximations of a deeper truth. A serene quest for cosmic clarity, patiently awaiting our deeper inquiry with an invisible yet undeniable power. Its quiet majesty. Cosmic unknown, embracing the unseen and finding serenity in the vast, gentle rhythm of the cosmos. As our tranquil journey through the cosmic, silent voids draws to a close, we are left with a profound sense of the universe's quiet majesty. We have traversed the unseen embrace of dark matter that cradles our Milky Way, explored the intricate dance of its satellite galaxies, and contemplated the relentless, accelerating expansion of the voids driven by dark energy. These hidden realms, far from being mere emptiness, are vibrant, dynamic participants in the cosmos's grand narrative, silently shaping the luminous tapestry we perceive. The knowledge that our galactic home is intricately woven into this larger, mostly invisible architecture, guided by forces still largely beyond our full comprehension, can evoke not a sense of insignificance, but rather a deep, abiding wonder. It reminds us that the universe is a place of endless discovery, where the boundaries of our understanding are constantly expanding, and where every answered question often reveals a new, more profound mystery. We are privileged to exist in an epoch when we can begin to decipher these cosmic whispers, to map the unseen, and to contemplate the vast, elegant interplay of forces that define all of existence. May these deep thoughts about the hidden grandeur above and below our Milky Way carry you into a world of tranquil sleep. Remember that the universe is an astonishing place, full of silent wonders and unseen connections, and you are, in every sense, a precious and aware part of it. Fall asleep with this feeling of serenity and endless knowledge, knowing that even in darkness, there is profound structure and quiet beauty. Good night. The initial concept many of us naturally form when contemplating the edge of the universe is often one of a tangible boundary, a cosmic wall, or an ultimate barrier beyond which there is simply nothing. We are accustomed to finite objects in our daily lives: a room with 4 walls, a book with pages that eventually end, a planet with a discernible surface that defines its extent. It is a deeply ingrained intuition to imagine limits in a spatial sense, perhaps picturing a vast dark expanse that abruptly terminates like the edge of a flat map, or even a literal cliff into an unknowable void. But the cosmos, in its grand and often profoundly counterintuitive design, transcends these familiar geometric constraints. The universe, in a truly profound and scientifically informed way, does not possess such a physical edge, a point where space simply ceases to be, or where one might hypothetically fall off into an absolute nothingness. Instead, what we perceive as a limit, a boundary to our cosmic view, is not a wall in space, but rather a profound and ever-shifting horizon in time. This horizon, often referred to as the observable universe, is a direct and inescapable consequence of 2 fundamental and deeply interconnected principles that govern the very fabric of our reality: the finite age of the universe itself and the constant, immutable speed of light. Light, that tireless and ubiquitous messenger of all visual information, travels at an astonishing yet ultimately finite speed of approximately 300,000 kilometers per second in the perfect vacuum of space. This fundamental constant, a cornerstone of modern physics, first elucidated by the profound insights of Albert Einstein in his theories of relativity, and rigorously confirmed by countless experiments and astronomical observations since, represents the absolute cosmic speed limit for any information or influence within our cosmos. There is, quite simply, no faster way for data, for events, for the very essence of what we observe, to traverse the immense cosmic distances between objects and ourselves. And since the universe itself is not eternal in its current dynamic form, but rather had a definite beginning, the Big Bang, an event estimated to have occurred approximately 13.8 billion years ago, the light from the most distant objects has only had that specific and finite amount of time to embark on its arduous journey across the expanding cosmos and ultimately reach us. Therefore, when we gaze into the deepest reaches of space with our most powerful telescopes, whether they be orbiting Earth or situated in remote terrestrial locations, we are not merely observing distant objects in their contemporary state. We are, in a very real and literal sense, gazing backward through the immense epochs of cosmic history. The light from a galaxy that is, for instance, 1 billion light-years away, presents that galaxy to us as it appeared 1 billion years in our past. The farther we extend our observational vision into the cosmos, the further back in time we are able to see, unfolding the universe's grand narrative, event by event, photon by photon. The edge of the universe, then, is not a physical frontier, a kind of impenetrable barrier that one might hypothetically encounter and peer over if one could travel far enough. Instead, It is a temporal boundary, a limit imposed by the very flow of time and the finite speed at which light travels. It is the furthest point in the past from which light has managed to embark on its journey across the immense cosmic expanse and finally arrive at our detectors, here on Earth, at this precise moment of observation. This ever-present limit defines our observable universe, a vast luminous sphere geometrically centered on us, the observers, stretching outward in every direction to the maximum distance from which light emitted at the dawn of time is only now making its arrival. Beyond this immense horizon, there might indeed be more universe, more galaxies, more intricate structures of matter and energy, perhaps even an infinite continuation of space-time. But their light simply has not had enough time to complete its arduous. The light from those most ancient of cosmic events, a journey spanning billions of years to reach our sensitive instruments, thus defines the very limits of what we can, in principle, ever hope to observe. This boundary, this cosmic horizon, is not static. It is constantly expanding as the universe ages, and more light from ever more distant regions has the opportunity to finally reach us. Yet it remains a horizon, a fundamental limit to our perception, a profound reminder that our view of the cosmos is always, intrinsically, a view into its past. And it is important to understand that this observable universe is not a singular, absolute entity that encompasses all of existence. Rather, it is inherently a personal and subjective sphere, centered precisely on the observer. Just as a ship on the vast ocean has its own horizon, which moves with the vessel, so too does every point in the cosmos possess its unique observable universe. An observer positioned many millions of light years away from us would perceive a different set of galaxies and structures within their own observable sphere, many of which would lie beyond the reach of our current observations, and vice versa. They would be looking back in time from their own vantage point, witnessing a different tapestry of cosmic history. This concept carries a deep implication. There is no universal now in the cosmos that all observers can agree upon. The very fabric of space-time, as revealed by Einstein's relativity, tells us that simultaneity is not absolute. What is now for us here on Earth is not simultaneously now for an alien civilization in a distant galaxy. Their now could be our distant past or our far future, depending on their motion and gravitational environment. This means that the observable universe is not merely limited by light travel time, but also intricately tied to our specific position and timeline within the grand, four-dimensional expanse of space-time. It is a dynamic, evolving boundary, constantly expanding and shifting as the universe continues its grand, accelerated expansion. This expansion of space itself plays a crucial role in shaping our cosmic horizon. As the universe stretches, the very space between galaxies expands, carrying them further apart. This stretching also affects the light traveling through it. A photon emitted by a distant galaxy billions of years ago on its long journey towards us has its wavelength stretched or redshifted by the expansion of space. This redshift means that the light arrives at Earth with a longer, redder wavelength and consequently less energy. For objects far enough away, the expansion of space can be so rapid that the light emitted from them is stretched to wavelengths so long, so low in energy, that it becomes effectively undetectable by our instruments. This phenomenon further reinforces the idea of a horizon, not just of light travel time, but also of detectability. The light from some regions, though it may have had enough time to reach us, has been stretched beyond our capacity to observe it meaningfully, fading into a cosmic whisper. The deepest, most ancient edge we can truly observe is the cosmic microwave background, or CMB. This is not light from stars or galaxies, but rather the relic radiation from the universe's infancy, a faint uniform glow permeating all of space. It originated about 380,000 years after the Big Bang, a moment when the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms. Before this epoch, the universe was a dense, hot plasma, opaque to light, much like a thick fog. Photons were constantly scattering off free electrons, unable to travel far without colliding. But once the neutral atoms formed, the universe suddenly became transparent, allowing light to stream freely for the very first time. This first light, now redshifted to microwave wavelengths due to billions of years of cosmic expansion, provides us with a direct image of the universe when it was a mere fraction of its current age. It is, in essence, the visual boundary of our universe, the furthest back in time we can possibly see, a snapshot of the primordial cosmos. So, when we speak of the edge of the universe, we are not speaking of a physical barrier in space, but rather a profound temporal boundary, a visible horizon beyond which the light has not yet had time to reach us or has been stretched beyond detection. This boundary is defined by the age of the cosmos and the speed of light, and it is a horizon that, in a deeply personal sense, surrounds each and every observer. The universe beyond this horizon remains an enigma, a realm that is, for now, forever beyond our direct observation, a silent, unseen expanse whose full nature continues to inspire our deepest scientific inquiries and our most tranquil contemplations. While the cosmic microwave background provides a profound visual boundary, a luminous echo from the universe's earliest moments, it is crucial to understand that this horizon does not, in fact, signify the physical edge of space itself. The universe in its entirety is almost certainly far grander and more expansive than the portion we can currently observe, or indeed will ever be able to observe directly. Our observable universe is merely the spherical region from which light has had sufficient time to reach us since the Big Bang. Beyond this sphere lies the unobservable universe, a vast expanse of cosmic structures, galaxies, and perhaps even entirely novel phenomena, whose light has simply not yet completed its journey across the ever-expanding cosmic distances to our location. It is akin to standing in the middle of a dense, ancient forest. You can only see as far as the trees allow, but you know that the forest continues far beyond your immediate line of sight. Scientists, through a combination of theoretical models and observational data, have come to believe that the true universe, the actual universe, extends far beyond our 13.8 billion light-year observational limit. One of the most compelling theories supporting this idea is cosmic inflation, a concept developed in the early 1980s by physicists such as Alan Guth. Inflation posits that in the merest fraction of a second immediately following the Big Bang, space underwent an incredibly rapid exponential expansion, stretching far faster than the speed of light itself. This was not the movement of objects through space, but the expansion of space itself, carrying all matter and energy along with it. This theory elegantly resolves several long-standing cosmological puzzles, including the apparent flatness and homogeneity of the universe on large scales. If inflation did indeed occur, it would have stretched any initial curvature of space to an almost perfectly flat state, much like inflating a small, wrinkled balloon to an enormous size makes its surface appear smooth and flat to an observer on it. This notion of a spatially flat universe is strongly supported by precise measurements of the cosmic microwave background, which reveal subtle temperature fluctuations that are entirely consistent with a flat geometry. In a spatially flat universe, parallel lines would remain parallel forever, and the angles of a triangle would sum precisely to 180 degrees, just as they do in Euclidean geometry. Such a universe, if infinite in extent, would have no spatial edges whatsoever. You could, in principle, travel in any direction indefinitely without ever encountering a boundary, a wall, or a point where space simply ends. This is a strikingly different image from the finite, bounded universe our everyday intuition might suggest. It implies a cosmos that, while having a temporal beginning, may well be boundless in its spatial dimension, stretching into an ultimate infinity, without any discernible center from which it expands. The Big Bang, therefore, was not an explosion in space, but rather the simultaneous emergence and expansion of space everywhere. The idea that the universe has no center is as important as the idea that it has no edge. When we observe distant galaxies rushing away from us, it is not because we occupy a privileged central position from which everything else is receding. Rather, every point in the universe experiences the same phenomenon. All other points appear to be moving away from it, much like dots on the surface of an inflating balloon. From the perspective of any dot, all other dots appear to recede, yet there is no single center on the surface of the balloon. Similarly, in our three-dimensional universe, every galaxy sees every other galaxy receding, and no specific location holds the distinction of being the cosmic center. This profound symmetry reinforces the absence of a spatial edge, as a universe without a center inherently lacks a reference point from which an edge could be defined. To contemplate a universe without a physical edge, a cosmos that simply extends without termination, can evoke a sense of serene awe. It suggests that our limited perception, shaped by the finite speed of light and the universe's own history, merely reveals a small, albeit magnificent, chapter of a much larger, perhaps endlessly unfolding, cosmic story. Our horizon is a boundary of knowledge, not of existence, a gentle reminder of the vastness that lies just beyond our current reach, inviting us to ponder the boundless possibilities that may reside in the unobservable depths of time and space. If space itself is without boundaries, stretching perhaps infinitely, then what does that imply for the future of our cosmic view? This profound thought leads us to another fascinating and somewhat mysterious aspect of our cosmos: dark energy. For decades, scientists expected the universe's expansion to gradually decelerate over cosmic time, a natural consequence of the gravitational pull exerted by all the matter within it. However, a startling discovery made in the late 1990s by two independent teams of astronomers revealed precisely the opposite. The expansion of the universe is not slowing down. It is, in fact, accelerating. This means that the rate at which galaxies recede from one another is increasing, a phenomenon attributed to a pervasive, enigmatic force that we have named dark energy. Dark energy, comprising approximately 68% of the universe's total energy matter content, acts as a kind of anti-gravitational force, subtly pushing space-time apart. Its precise nature remains one of the most profound unsolved mysteries in physics, but its observable effects are undeniable. This accelerating expansion profoundly impacts our understanding of the cosmic horizon. While the particle horizon defines the boundary of what we can currently see due to age, the accelerating expansion introduces another, more permanent boundary: the cosmic event horizon. The cosmic event horizon represents the ultimate limit of what we will ever be able to observe, even if we were to wait an infinite amount of time. Due to dark energy's relentless push, galaxies beyond a certain distance are already receding from us at speeds greater than the speed of light. It is important to clarify that these galaxies are not moving through space faster than light, which would violate Einstein's special relativity. Instead, the space between us and them is expanding so rapidly that their apparent recession velocity exceeds light speed. For light emitted from these increasingly distant regions, the journey towards us becomes a losing race. Even if a photon sets out in our direction, the space it needs to traverse stretches faster than the photon can cover it. It is as if the light is trying to swim upstream against an ever-strengthening current, destined never to reach the shore. This means that over immense cosmic timescales, as the acceleration continues, more and more galaxies will cross this cosmic event horizon, falling out of our observable universe forever. Their light, once visible, will become too red-shifted, too faint, and too far behind the ever-stretching fabric of space to ever reach us. Imagine a future, billions upon billions of years from now, where the night sky, once ablaze with the myriad lights of countless galaxies, becomes a vast, empty darkness. Only the galaxies within our immediate gravitationally bound group, like the Andromeda Galaxy and the Milky Way, will remain visible, eventually merging into a single, colossal supergalaxy. All other galaxies, once dazzling points of light, will have receded beyond our cosmic event horizon, their light forever lost to our view, leaving behind a profound cosmic solitude. This profound cosmic solitude, though distant, offers a quiet reflection on the ephemeral nature of our current, vibrant cosmic view. Our existence coincides with a unique epoch in cosmic history, a fleeting window where the universe is both old enough for complex structures like galaxies and stars to have formed, and young enough for their light to still reach us across vast distances. Future civilizations, if they exist in this far-off, accelerating universe, would inhabit a cosmos drastically different from ours, a universe where the evidence of distant galaxies, and indeed the very notion of a Big Bang as a universal event, might be all but erased from their observable sky. They might even conclude that their local supergalaxy is the entire universe, unaware of the vast, unseen expanses that have long since slipped beyond their perception. This cosmic isolation, therefore, becomes a horizon not just of observation, but potentially of knowledge itself, shaping the understanding and philosophical outlook of any intelligence that might arise in those distant, lonely eons. It underscores the preciousness of our present cosmic moment, where the universe still largely reveals its grand history to us. The concept of a cosmic event horizon, where distant galaxies recede irrevocably beyond our observational grasp, invites us to contemplate the very nature of reality itself. If entire swathes of the cosmos are destined to become forever unobservable, does their existence somehow diminish for us? This is not merely a technical limitation of our instruments, but a fundamental feature of a universe governed by accelerating expansion. It means that the universe we perceive, the one we construct our models around, is always a partial picture, a snapshot from our unique vantage point in space and time. Our observable universe, then, is a bubble of information, constantly expanding but simultaneously losing content at its fringes as distant light struggles against the accelerating cosmic tide. This dynamic interplay between expansion and observation forces us to consider the limits of our knowledge, not just of physical space, but of the entire cosmic narrative. It paints a picture of a future where even the most advanced civilizations, equipped with technology far beyond our current imagining, might find themselves in an increasingly barren sky, unable to trace their cosmic origins or the grand evolutionary path of the universe, simply because the evidence has drifted beyond their reach, carried away by the relentless stretching of space. This quiet, inexorable fading of the cosmic tapestry is a profound thought, suggesting that our current epoch, with its rich, observable cosmos, is a unique, fleeting moment in the universe's long story, a period of maximum cosmic visibility. It is a precious, transient clarity before the encroaching veil of the unobservable deepens, a reminder of the universe's ceaseless transformation. Consider for a moment the fundamental constants that underpin our universe: the speed of light, the strength of gravity, the masses of elementary particles, and the charge of an electron. These values, meticulously measured and incorporated into our physical laws, define the very character of our reality, allowing stars to form, elements to fuse, and life to emerge. They are the fixed parameters of our cosmic home. But what if, beyond our cosmic event horizon, in those regions forever inaccessible to us, these constants were subtly, or even dramatically, different? While our current understanding of physics suggests a uniform set of laws throughout the observable universe, the possibility of variations in the unobservable regions remains a fascinating, albeit speculative, area of inquiry. Some theoretical frameworks, particularly those arising from inflationary cosmology and string theory, propose the existence of a multiverse, an ensemble of many universes, each potentially possessing its own unique set of physical laws and constants. This idea, often termed the cosmic landscape, suggests that our universe is just one of an immense number of possible universes, each born from a different outcome of the inflationary process, with its own distinct physical parameters, perhaps even a different number of spatial dimensions. The edge of our universe, in this context, then transforms from a mere temporal boundary of perception into a conceptual boundary separating one set of physical laws from another, a transition point into an entirely different realm of existence where the very rules of reality are reimagined. In such a grander cosmic tapestry, our universe would be but one thread, one bubble in a vast, ever-foaming sea of nascent realities. Each of these neighboring universes, if they exist, would be entirely causally disconnected from our own, meaning no information, no light, and no influence could ever pass between them. They would represent true beyonds, not in a spatial sense of being outside our universe, but as completely separate, self-contained space-time continua, each evolving according to its own intrinsic logic. This moves the concept of an edge from a boundary within our universe to a boundary between universes. It's a shift from thinking about the limits of our space to thinking about the limits of our reality, our particular set of physical laws. The edge then becomes a theoretical interface, a conceptual boundary where our known physics might cease to apply, giving way to entirely different rules of existence, perhaps even different fundamental dimensions or forms of matter we cannot yet conceive. This radical idea, while not directly testable with current technology, offers a profoundly expansive vision of the cosmos, suggesting that the nothingness beyond our observable horizon is not an empty void, but potentially an infinite array of other somethings, each with its own beginning, its own evolution, and perhaps its own intelligent observers, each a distinct cosmic narrative playing out in parallel. This perspective transforms our horizon from a barrier into a window, albeit a theoretical one, onto an unimaginable diversity of physical realities. It suggests that our quest to understand the edge of the universe is not just about mapping distances, but about grappling with the fundamental nature of existence itself, questioning whether our reality is singular or merely one of countless possibilities, each unfolding its own unique cosmic drama. Furthermore, some cutting-edge theories, like the holographic principle, add another layer of abstract complexity to this notion of a boundary. This principle, derived from studies of black holes and quantum gravity, suggests that all the information contained within a volume of space could be encoded on a two-dimensional surface enclosing that volume, much like a hologram. If this principle applies to the universe as a whole, then perhaps our three-dimensional reality is itself an emergent phenomenon, a projection from a deeper two-dimensional informational surface. In this view, the edge of the universe could be thought of not as a physical location, but as the very surface on which the fundamental data of our cosmos is written, a kind of cosmic canvas from which all appears to emerge. It is a boundary of information, a deeper layer of reality from which our familiar three-dimensional world arises, a subtle yet powerful reshaping of what we perceive as fundamental. This adds a profound, almost mystical dimension to our understanding of cosmic limits, suggesting that the universe's edge might be less about reaching a distant point and more about uncovering a deeper informational structure, an elegant code that defines our very existence. This contemplation of the unobservable, the potentially infinite, and the existence of other realities can be deeply calming. It places our individual existence within a context of immense scale and profound mystery, suggesting that our personal horizons, the limits of our own understanding and experience, are but reflections of the grander cosmic horizons. We are part of a universe that is constantly revealing itself, yet always holding secrets beyond our immediate grasp. This constant unfolding, this dynamic interplay between what we know and what we can only imagine, is a beautiful reminder of the endless journey of discovery that defines both science and our own conscious experience within the cosmos. To acknowledge the limits of our perception is not to admit defeat, but to embrace the boundless wonder of what lies beyond, fostering a peaceful sense of humility and interconnectedness with the grandest scales of existence. The edge, then, is not an ending, but an invitation to quiet contemplation of the infinite, a silent promise of deeper understanding yet to be unveiled, a gentle whisper from the unseen reaches of creation that reminds us of the endless possibilities woven into the very fabric of being. Our finite observations merely scratch the surface of an unbounded, magnificent cosmic ocean. And in that humbling realization, we find a tranquil beauty, a deep sense of belonging within the vast, intricate design of all that is. We are not just within the universe, we are a part of its continuous, mysterious unfolding, forever bound by its horizons, yet endlessly seeking what truly lies beyond. Human mind, in its remarkable capacity for abstraction and introspection, often seeks to draw maps and boundaries, to define and delineate the extent of its understanding. Yet the universe consistently challenges these innate tendencies, demonstrating that the most profound truths often reside in concepts that defy simple visualization or categorical partitioning. The edge of the universe, as a horizon in time, embodies this challenge perfectly. It is a boundary that expands with our knowledge, yet always keeps a step ahead, ensuring that a realm of the unknown persists. This perpetual state of discovery, this endless frontier, is not a source of frustration, but of enduring wonder. It signifies that the cosmos is not a solved puzzle, but a living, breathing mystery that continues to evolve, to unveil new layers of complexity and grandeur. And in that continuous unveiling, we find a mirror to our own growth, our own journey of learning and becoming. The universe, in its very structure, encourages us to remain open to the unexpected, to embrace the subtle shifts in our understanding, much like observing the slow, majestic dance of celestial bodies across the night sky. Each new observation, each refined theory, pushes our horizon a little further, revealing more of the universe's intricate beauty, while simultaneously reaffirming the immensity of what remains unobserved. This delicate balance, this dance between the known and the unknown, is what makes the study of the cosmos so deeply enriching, so profoundly calming to the inquisitive mind. It invites us to let go of the need for absolute finality and instead to find peace in the journey of perpetual exploration. The journey into understanding the universe's edge as a horizon of time and information rather than a physical barrier profoundly reshapes our perception of reality. It moves beyond the simple notion of space ending somewhere, pushing us towards an appreciation of the intricate interplay between light, time, and the very act of observation. This is a crucial distinction, for it means that the edge is not an inherent property of the universe's ultimate physical extent, but rather a dynamic boundary defined by our ability to perceive and gather data. We are, in essence, constantly situated at the center of our own observable bubble, a sphere whose radius is determined by how far light has traveled to reach us since the cosmic dawn. And this bubble, as we discussed, is not merely expanding. It is also losing content due to the accelerating expansion driven by dark energy, ensuring that some distant regions will forever remain beyond our sight. This constant push and pull creates a unique intellectual landscape. It highlights that our comprehension of the universe is fundamentally tied to the information that reaches us. Every photon carries a story, a message from a particular moment in cosmic history. When that message can no longer reach us due to the immense distances or the stretching of space-time, a part of the universe simply becomes unknowable to our direct senses. This isn't a flaw in our understanding, but a built-in feature of a relativistic, expanding cosmos. It's a gentle reminder of the universe's grand indifference to our desire for complete knowledge, yet also an invitation to find peace in the partial, the evolving, the always more to discover. The edge is, in this sense, a continuous challenge to our intellectual curiosity, a silent promise of endless inquiry. It is a boundary that recedes, yet always inspires, ensuring that the scientific endeavor remains vibrant and ever-expanding, much like the universe itself. The universe does not present itself as a completed book, but as an unfolding epic where each new chapter pushes the narrative further into realms previously unimagined. This realization that the edge is a horizon intimately linked to our perspective deepens our connection to the cosmos. It implies that our individual now is a unique slice of space-time, and our observable universe is uniquely ours. While the laws of physics are universal, the specific manifestation of the universe as observed is local. This personal horizon means that every conscious being, wherever and whenever they exist in the vastness of the cosmos, experiences their own unique boundary of perception. There is no single objective edge that all beings would agree upon, because each observer is at the center of their own cosmic sphere. This is a profound departure from older, more static models of the universe, which often posited a fixed, universal boundary. Instead, we find ourselves in a dynamic, relativistic cosmos, where the concept of a limit is fluid, observer-dependent, and deeply intertwined with the passage of time itself. This is not a cause for disorientation, but for a calm appreciation of the universe's intricate design, where even the most fundamental aspects of reality are shaped by perspective. It encourages a sense of individual significance within the cosmic whole, recognizing that your unique point of observation is as valid and central as any other. It suggests that the quest for a definitive edge is perhaps a misplaced endeavor, as the very act of seeking defines the boundary itself. Rather, we are invited to embrace the provisional nature of our cosmic map, knowing that its contours are drawn by the very act of looking. The very act of seeking this edge, this ultimate boundary, becomes less about reaching a physical destination and more about pushing the limits of our conceptual frameworks. It is a constant refinement of our understanding of space-time, gravity, and the very nature of existence. This intellectual pursuit, while challenging, is also deeply meditative. It allows us to transcend our immediate terrestrial concerns and engage with questions of ultimate scope, finding a quiet satisfaction in the expansion of our mental horizons, even as the cosmic horizon remains just beyond our full grasp. The journey of scientific discovery, in this light, mirrors a spiritual quest, a continuous striving for deeper insight into the fundamental truths of being. The universe, in its boundless mystery, offers an endless canvas for such contemplation, inviting us to find serenity in the pursuit of knowledge itself. We are not just passive observers, we are active participants in this cosmic unfolding, our consciousness a tiny yet significant part of the universe's awareness of itself. And in that awareness, we find a tranquil resonance with the vastness that surrounds us, a gentle reminder of our intrinsic connection to the grand cosmic dance. Our minds, in their capacity to ponder such immensities, are themselves a testament to the universe's capacity for self-reflection. They are a delicate instrument through which the cosmos itself begins to understand its own intricate design and its own profound limits. Furthermore, the concept of a beyond our observable universe, a realm from which light has not yet reached us, or perhaps never will, is not an empty void, but a region of profound potential. It represents the unknown that fuels scientific inquiry, the vast expanse awaiting future discoveries, future theories, and perhaps even future forms of observation we cannot yet envision. This unobservable cosmos is not a place of existential dread, but a reservoir of possibility, a silent promise of further revelations. It allows us to imagine a universe that is not constrained by our current limitations, a universe that continues to unfold in ways that may forever surprise and inspire us. This open-endedness, this inherent incompleteness of our current cosmic map, is a source of serene excitement, a gentle nudge towards humility and continuous learning. It reminds us that our story and the story of the universe is far from over, always evolving, always offering new wonders to explore, even if only in the quiet chambers of our minds. The edge of the universe is thus not an ending, but a perpetual beginning, a constant invitation to wonder and to dream, fostering a deep sense of calm in the face of the truly immense. We are forever at the threshold of the unknown, and in that threshold we find a peaceful, boundless expanse for our thoughts to wander and our understanding to grow, a gentle lullaby from the depths of time. This profound sense of a continuous, unfolding mystery is not a burden, but a liberation, freeing us from the need for absolute certainty and opening our minds to the endless dance of possibilities. It is a quiet testament to the universe's infinite capacity for self-revelation. This journey of conceptualizing the universe's non-physical edge, this horizon of time, ultimately brings us back to ourselves, reminding us that our own lives, in their fleeting beauty, are contained within a personal horizon of birth and death. And just as the cosmic horizon defines the limits of what we can see of the universe, our personal horizon defines the limits of our individual conscious experience. Yet within these boundaries, both grand and intimate, there is an infinite depth of meaning and connection. The atoms that compose us, the light that allows us to see, the very consciousness that contemplates these vast ideas, all are products of this same universe, woven into its ongoing story. To understand the cosmic edge as a temporal limit rather than a spatial wall is to embrace a deeper, more elegant truth about reality. It is to acknowledge that the universe is not a container with fixed sides, but an ever-evolving narrative, a grand, tranquil unfolding in which we are privileged participants. And in that participation, in that quiet contemplation, we can find a profound peace, a sense of belonging within the boundless mystery. The profound journey we have undertaken, contemplating the universe's edge not as a physical barrier, but as a dynamic horizon in time, brings us to a quiet realization about our own place within this cosmic narrative. This temporal boundary, constantly shifting and expanding, is not a sign of the universe's finitude, but rather a testament to its immense, perhaps boundless, extent, and our limited yet ever-growing capacity to perceive it. It reminds us that our understanding is always provisional, a work in progress, much like charting an endless ocean from a single, moving vessel. The unobservable universe, the realm beyond the reach of light that has had time to travel to us, is not empty space. It is teeming with events, with galaxies forming and evolving, with cosmic dramas unfolding, all just beyond the threshold of our direct perception. These distant events are real, they are happening, but their light, their information, is still on its arduous journey, or has been irrevocably stretched by the accelerating expansion of space, destined never to arrive. This subtle distinction between what exists and what is observable encourages a profound humility in our scientific endeavors, a recognition that the universe holds secrets that may forever whisper just beyond our grasp. It is a beautiful paradox. The more we discover, the more we become aware of the immensity that remains undiscovered, deepening our sense of wonder rather than diminishing it. This constant interplay between the known and the unknown fosters a tranquil curiosity, an invitation to embrace the mystery as an intrinsic part of existence itself. Our current epoch in this grand cosmic ballet appears to be a uniquely privileged moment. We exist at a time when the universe is old enough for complex structures like stars, planets, and even life to have emerged, yet young enough that the light from a vast number of these distant galaxies is still within our observable horizon. Future civilizations, if they arise in the far distant eons when dark energy has further stretched the fabric of space, may find themselves in a profoundly different cosmos. Their night sky could be largely empty, devoid of the myriad galaxies that currently populate our view, leaving them with an impoverished cosmological record. They might struggle to reconstruct the early universe, to understand the Big Bang, or even to conceive of the vast interconnected cosmic web that we observe today. This thought, while tinged with a gentle melancholy for the future, underscores the preciousness of our present cosmic vista. It is a reminder to cherish this fleeting window of clarity, to absorb and contemplate the universe's grandeur while it is still so richly displayed before us. The light reaching us now is a relic, a whisper from a bygone era, carrying tales of cosmic evolution that will eventually fade into an ultimate, unobservable silence for those who come after. This passing of information, this slow retreat of the cosmic past, is a poignant illustration of time's relentless flow, shaping not just the universe, but our very ability to witness its story. It teaches us that our perception of the cosmos is a temporary gift, a unique perspective from a particular moment in the universe's grand unfolding. The tools of theoretical physics, armed with mathematics and sophisticated models, allow us to peer beyond this observational veil, to infer the existence and properties of the unobservable universe. We extrapolate from the laws we observe, from the subtle patterns in the cosmic microwave background, and from the dynamics of galaxy clusters to construct a coherent picture of a cosmos that extends far beyond what light can currently show us. These models, such as those describing cosmic inflation or the large-scale structure of the universe, are not mere speculation. They are rigorously tested against all available data, providing the most consistent and elegant explanations for the universe's observed features. They are our intellectual instruments for traversing the unobservable, for painting a picture of a universe that is truly without spatial bounds. A universe where the Big Bang occurred everywhere simultaneously, without a central point or an external outside into which it could expand. This reliance on inference and mathematical beauty, rather than direct observation for the furthest reaches, is a sophisticated form of seeing, a seeing with the mind, guided by logic and consistency. It is a testament to the power of human intellect to grasp concepts that lie beyond the direct reach of our senses, fostering a deep sense of intellectual satisfaction and a tranquil confidence in the predictive power of science. This process of building models to describe the unseen is, in itself, a form of cosmic poetry, where equations become the language of ultimate truth, allowing us to conceptualize the vastness that remains forever just out of sensory reach. Ultimately, understanding brings us to a deeply personal reflection. Our own lives are defined by a personal horizon, a span of time from birth to eventual rest. Within this span, we gather information, form memories, and construct our own understanding of the world. Just as the cosmic horizon limits our view of the universe's totality, our personal horizon limits our individual conscious experience. Yet within these defined boundaries, whether cosmic or personal, lies an infinite depth of meaning, connection, and potential for wonder. The very atoms that constitute our bodies were forged in the hearts of ancient stars, scattered across the cosmos, and eventually gathered to form our planet and ourselves. The light that allows us to see, to learn, to contemplate these vast ideas, is a continuous thread connecting us to the universe's grand narrative. Our consciousness, in its remarkable ability to ponder these immensities and to find beauty in the unknown, is itself a product of this cosmic unfolding, a fleeting yet profound expression of the universe becoming aware of itself. In this tranquil awareness of our interconnectedness, in this acceptance of horizons both vast and intimate, we can find a profound sense of peace. The universe, in its boundless, edgeless expanse, does not demand a final answer, but invites continuous contemplation, a gentle, unending journey of discovery. And in that journey, we can allow our minds to drift, knowing that even as we rest, the cosmos continues its majestic, silent dance, holding infinite wonders both seen and unseen, forever just beyond the horizon of our present moment. This sense of belonging to an eternal unfolding mystery, even in its partial revelation, is the true calm that the study of the universe offers, a silent lullaby woven from the fabric of space-time itself. Universes. May these deep thoughts about the universe's edge, not as a boundary in space, but as a profound horizon in time, carry you into a world of tranquil sleep. As we drift through the cosmic night, Remember that our observable universe is a precious, fleeting glimpse into an immense and perhaps boundless reality, a tapestry woven from light and time. The unseen depths, the realms beyond our current perception, are not empty voids, but rather realms of unending potential and mystery, a silent promise of discoveries yet to unfold. Consider the gentle rhythm of the cosmos, its ceaseless expansion, and the patient journey of ancient light. In this grand, evolving narrative, our own existence, our own brief moment of consciousness, is intricately connected to the stars and the very fabric of space-time. We are, in a profound sense, the universe experiencing itself, contemplating its own magnificent, edgeless expanse. May you fall asleep with this feeling of serene wonder, embracing the beautiful paradox of a cosmos that is both knowable and eternally mysterious. Rest in the knowledge that you are a part of this amazing dance, a conscious flicker within the infinite unfolding. Good night.